Hello, everybody. I hope you can hear me. It looked like there was something wrong with my really nice microphone. So somebody tell me in chat if you're able to hear me right now. Well, oh, good. Thank you very much, Braxton. That's good to know. Welcome, everybody. Anybody heard any news lately? Anything big going on down here in human society? Yeah, well, we won't be getting into that. We'll be considering somewhat larger topics tonight, specifically life, the universe, and everything. So thank you for joining us on this first night after the election here in the United States. I'm going to look through the list now, watching for us to be joined by our very special guest, Sara Imari Walker. And here she is. Sara, I'm going to promote you now, bring you in as a speaker. I, of course, am Matt Kaplan, the Planetary Society's Senior Communications Advisor, former host, creator of Planetary Radio for 20 years. And there is Sara. Welcome.
Hi.
Hi, it's great to see you again.
Nice to see you too.
So just getting underway here, I think it's going to be a very busy hour. We apologize to anybody who may have been a little bit confused because of the mistake that was made in our newsletter that said that this was happening on Monday. I did hear from a couple of you who said, oh, we saw that and we hope to be able to join you tonight. And if you are joining us by watching the recording after the fact, welcome. Some of you, of course, are members of the Planetary Society. Many of you are not. If you're not, please consider joining us. One of the things that you'll be able to do is join us live here in our member community, and that means that you'll be able to contribute to live conversations like this, along with all of the other wonderful benefits of being part of the Planetary Society, which is nearing its 45th anniversary as an organization here on this pale blue dot. Planetary.org is where you can learn more, but we welcome all of you this evening. And having said that, I'm going to move my camera a little bit. God, that picture looks, I don't know, I look a little washed out, but Sara, you look great. Again, welcome. I've already told you how much I loved this book. And we've been hearing a lot of that from our other members as well. So thank you up front for presenting this.
Yeah, thanks for having me here tonight. I'm really excited to talk with everyone.
Let me tell you a little bit about Sara. Now, I hope that all or nearly all of you have read the book, because otherwise some of the conversation tonight may be a little bit hard to follow. This is, after all, the Planetary Society Book Club, but hopefully you'll all be able to tag along. If you missed the information about the author, here's a little thumbnail. Astrobiologist and theoretical physicist Sara Imari Walker is Deputy Director of the Beyond Center at Arizona State University. Professor Walker is also Deputy Director of the ASU SFI, or Santa Fe Institute Center. As some of you know, the Santa Fe Institute comes up in her wonderfully stimulating and entertaining book published just this year. Here's the full title: Life as No One Knows It, The Physics of Life's Emergence. And it's actually even much more than that. In 2021, she received the Stanley Miller Early Career Award from the International Society for the Study of the Origin of Life. She was recently the guest of our good friend and former board member, Neil deGrasse Tyson, on Star Talk. And she was heard just recently on the show for another guy, Joe Rogan, something, I think that's the name, talked with her for nearly 3 hours. And Sara, I promise we won't repeat that or equal that here this evening.
Excellent.
Although it was pretty interesting. I can't say I did skip around, but I did hear a good piece of that. And the rest of you, I hope you know, if you are with us live, you can join us in the chat, where Amber Trujillo, the manager of the digital community, is following along, and she'll be posting nice links there. You can see them popping up in the chat right now. Post your questions and comments for Sara there, and I will try to get to a lot of them. Sara, I have condensed 15 pages into 2.5.
Oh, wow.
And I didn't have a tie that screamed life but I
Oh,
decided, well, looking out across the
I
galaxy,
like
maybe.
that one. That's a good
Thank you.
choice.
Thank you very much. Here's one of the many passages in this book that either made me smile or say, huh?
Mhm.
And this one did both. Here's the quote. In this book, we are after a theory with high explanatory power that will provide new, deeper insights into the nature of life. Incidentally, the fact that explanatory theories work in physics and science more broadly is itself an important clue into the nature of life. Life is, after all, the only kind of physical system we know of that can write down explanations like the laws of physics. I really love that.
Thanks. Yeah. I think one of my favorite things to think about when we're thinking about the nature of life in the universe is that we can't decouple ourselves from that. So I think it's a really important lens through which to see these problems. And also, it's one other thing that, like, I just to kick off that I think is really important is that kind of example. I guess I like to use because I think it juxtaposes our current explanations with what's necessary to explain something like us trying to explain the rest of it.
And a difficult thing to do, right? As you point out in the book, since we are inside the universe, it's a little tough to always understand ourselves because we can't stand outside ourselves.
That's right. That's absolutely right.
Here's a question that has come up repeatedly as I've talked with lots of astrobiologists over the years. Why is it so damn hard to define life?
Yes, so I think this is an excellent question. And a lot of what I talk about in the book, and I've also just thought this for years, that defining life is not exactly the right approach to solve the problems that we have to deal with in science. So I'm very much a questions first, like how does life arise in the universe, or how would we identify life on another planet, rather than a priori like trying to define it and then doing those things. So I think the challenge has been that once you start trying to define life, you're putting boundaries around our current understanding and trying to put life as a category into that, rather than opening to the possibilities of broader explanations that might apply to alien life.
Don't you say at one point that maybe the question isn't what is life, but what does life do?
Yes. Yes. So I'm very much a fan of taking questions that have been traditionally really hard to answer, like what is life? And, you know, I talk a lot about the failures of certain definitions of life and why they haven't worked. And if you have that kind of thing for quite a while, in this case, many decades of people in my field trying to answer the origin of life, reframing the question often helps a lot. So my perspective on it has been to ask a different question is a better way to get to an answer faster than to ask the same question that we haven't been able to answer.
It does seem, as you point out in the book, it kind of follows that famous non-definition of pornography that I think was put forward by a Supreme Court justice. I don't know how to define it, but I know it when I see it.
Yes, yes, that was yeah. So there's there's also, like, if you go to astrobiology conferences, it used to be the case that people would quote this all the time because we know we don't have a good definition for life, yet we feel intrinsically like we will definitely know it when we see it. And so that comes from this old Supreme Court case that is kind of a bit of an interesting story. Yeah.
And then, I mean, you get deeply into, will we really know it if we don't take the kind of approach that you apparently are attempting to do, you and others, with assembly theory?
Yeah, so I think the challenge is if we have these sort of very earth-focused perspective on the problem and we're only looking at life as we know it, you know, we're looking for phenomena that occur elsewhere in the universe, alien life forms, and we might miss them entirely because we don't know how similar or different they should be to life on Earth. And so I think what I have always approached the problem as that there really is some fundamental missing understanding because we haven't solved the origin of life yet, and also because life poses all of these sort of very deep problems about that actually I think stand in like they're very contrary to like the way we think in traditional theoretical physics, or in the way we think about chemical organization. It confronts a lot of things, and none of them seem to be able to answer the question adequately, because we haven't solved the origin of life, and we actually really don't have a validated approach for life detection on other worlds. And so you might think like a molecule like DNA, which is critical to life on Earth, right, is a key memory storage for all life on Earth, including, you know, if you want to include viruses in your categorization of life. You know, that's a really complex molecule. And the complexity of it kind of suggests that it's actually itself the product of an evolutionary process, because it needs to be selected out of this very large space of different kinds of molecules that could emerge on a planet. And so the question for us had become, well, how would you actually identify the signatures of an evolutionary process anywhere in the universe that could generate such complex structures? And that's a much more general question. That became the motivation. So that's sort of the inversion from the what is life to why life became, or the what does life do, is we don't really know how to define life. I was interested in trying to derive the properties we associate to life from a much more universal understanding of the phenomena of life. And if we're thinking about looking for life on alien worlds, we're talking about a broad category of phenomena that happen on planets in the universe. And if they could be very different, not DNA based, for example, and build other kinds of complex structures on other planets, then we need to understand that physics much more universally. So this is where we got really interested in this idea of trying to fundamentally not only quantify, but actually figure out a way to measure complexity and use that as a sort of way of reframing the question of the nature of life and what it is.
That was a great introduction to a number of themes that are going to, I hope, are going to come up across the rest of our time together this evening. But I want to read another quote that I loved, which also addresses your own origins in this field. Here it is. I became more and more intrigued by the origin of life problem. It had none of the baggage or dogmas of conventional theoretical physics, and held all the things that attracted me to studying physics in the first place. In origin of life research, the ideas were on such tenuous theoretical footing that one could build a new understanding of reality from the bottom up, just as Isaac Newton had done for motion and gravity, James Clerk Maxwell for light, Charles Darwin for evolution. Emmy Noether, I believe I got it right, is for symmetries and conservation laws, and Werner Heisenberg and Erwin Schrödinger for elementary particles. As a PhD student, this was a risky thing to decide to spend your career on. And so to a degree, a smaller degree, this book is also sort of traces your progress in how you advanced in this field and what got you into it. It was, I mean, were you thinking at the time, do I really want to go down into this dark alley where physicists don't usually go?
Yeah, it wasn't quite like that. I have to say you did very well in the pronunciations. I read the audiobook and I had to like be very precise in all of these names. So I could like it was very funny. That's great. Yeah, it was about a very it feels like a very linear path, but it was a very non-linear path. So I think I wouldn't have known I ended up where I am working on the problems I am then. Although I wouldn't say it would be an unnatural sort of and like state where I am from where I started. But the way that I got into physics and science more generally was actually as a community college student. So my parents hadn't gone to university, and I just thought, oh, I'll go to community college. And I knew I liked science a little, so I just took all of the science classes. But I absolutely fell in love with physics. I just thought it was the most amazing subject, that we could, come up with mathematical theories that could describe very deeply the nature of reality. And in fact, as you come to study physics more, you see how much these sort of ideas that were developed in physics over centuries really have transformed and shaped the way we perceive reality, but also the kind of technologies we've developed and the way culture has evolved in kind of a deep way. And so I became really deeply intrigued by that. But as a typical physics student, I really thought, we already had a handle on the fundamental questions, and they were the things that were in my physics textbooks. And those were the exciting fundamental frontiers of physics. But it's interesting in retrospect, which I do talk about a lot in the book, is you're taught about the frontiers of previous generations because they become the standard knowledge of this generation. And I didn't get into the problem of the origin of life until I was a PhD student. And I was very resistant to it because I just thought it wasn't, it's like a typical sort of physicist, like biology is like a second order problem, like, I know experimental stuff. But when I was reading papers on it, it was just so clear that there was like this really open problem that no one knew how to ask the question, going back to like, you can get an answer for a question if you know how to ask it. And so the pieces are all there, but they hadn't been put together in the right way. And if you look at these sort of major shifts in our knowledge in the past, it was always, a certain generation of people came together and they figured out how to put the pieces together in a new way and come up with these broader, deeper explanations. And that's what I got in science for. And so that was sort of my transformation into thinking about the origin of life and really being excited about it, because it was more the creative pursuit of deep ideas that really got me into physics. And I think that's a really general approach to understanding how nature works. And it should apply in many areas that we maybe don't traditionally think of as physics. That might be, again, the physicist's ego. I don't know. But I think the problem of life, like if you're approaching it as an astrobiologist, you're asking about a universal phenomenon in the universe. And I think, and I also mentioned this, like we think that theories of quantum physics and general relativity are quite deep about the nature of reality. But again, it goes back to this idea, like we're the ones that generated those theories. So there's some structure the universe has built that comprehends the rest, which is, I'm sure many people here share that, sort of sentiment of wonder. And I guess I'm just so deeply interested in that part. Like what are the things like us and how are we part of this sort of universal fabric of whatever reality is? Yeah.
And going even beyond that, I mean, here is another one of those, really one of the most provocative paragraphs in the book. You said, personally, I'm convinced there is entirely new physics in the living universe, the part of reality that includes living things, awaiting our discovery. Or at least I'm convinced that adopting this view is more productive for gaining traction on hard problems like the origin of life or finding aliens than assuming there is nothing fundamentally new to discover in life. So is this the sort of pre-paradigmatic era that your close colleague Lee Cronin is talking about?
I hope so. I mean, I mean, part of the goal is, for many of us working on these problems that we want to see, we want to see interesting things happen in this space in our lifetime. Like, I really hope, I say this like very adamantly, I'm like, I hope the origin of life is solved before I die. But I really want to know. Yeah, I want to understand. And it's exciting to think, that science isn't a closed book, or our understanding is not a closed book. And I think this is actually critically important, because I think what we've seen, again, like appealing to the history of science, is every time we think we know everything, some new major revolution comes along and really transforms the way we think. Yeah. And I guess I've just thought, why not this century? I mean, we have so many things existentially happening with climate change and artificial intelligence that are kind of changing our perception of ourselves and our relationship to our planet, and the evolution of the planet as a whole. And we have these really deep problems we have not yet solved, like the nature of life, that I think it's a really exciting time to be working on fundamental problems.
I asked Arthur C. Clarke once, toward the end of his life, I said, if you were to place a bet on where some paradigm shattering innovation might come from, what would you look to? And I think he talked about vacuum energy, and he said there's something going on there that maybe has much more to tell us about how the universe really works. I think he probably would have loved considering that maybe life will be the key to unlocking something like this.
Yeah, it's interesting. That's really a great story. It's interesting to me how many people, look to sort of the edges of known physics as the next frontier in physics, is like really advancing these really fundamental questions. And I don't discount that. Like, I think there's a lot of frontiers in physics, and the way that we've been, developed our understanding of physics up to date has many questions open at the boundaries of our current understanding. But I think like it's got to be the case that these other areas have something to say. That's very fundamental. So I guess it's sort of, you know, one of the ones I like, there's always this idea of looking for like a grand unified theory, like can we merge general relativity and quantum physics? And this is going to teach us the deepest things about reality. And I am totally on board with that enterprise, and it, like some theories in that space actually end up being very similar to what I think about as far as fundamental structure of life, because they're related to causation and you know, like how does causal structure underlie the way the universe actually behaves. But the thing there that's interesting is, you know, again, I always think in the light of the history of physics, when you look at major advances, like why did we start down the road of developing quantum mechanics, or why did Einstein come up with the special theory of relativity? It wasn't because they were trying to unify existing theories or even trying to explain features of existing theories. It was there was some problem that they didn't have any explanation for. And so, you know, it's just interesting to me that there are areas where we have no paradigm. We don't have a paradigm for thinking about life in the universe. We have a lot of questions. We have a lot of disconnected areas of knowledge that are trying to start to build in that direction, but we don't have like a foundation in that area, and we have more questions than we have answers. So, I think there's open territory that hasn't been traditionally thought of from this kind of deep principles perspective that actually could offer a lot.
I love drawing that parallel between these areas where, you know, science hits a wall with classical physics, let's say, and, you know, that presented an opportunity. And yeah, it does sound, as you stated in the book and here, life may present that same sort of wall.
Yeah. I think it does. I mean, we can't make synthetic life in the lab.
Not yet, anyway.
Yeah, not yet, because we don't have the knowledge to do it. And you know, we're really, you know, the other one. So I work primarily in origins of life and thinking about life detection. We don't know how to detect life unambiguously on other worlds, and we don't know if we created life in the lab and it was a really different chemistry than life as we know it. Like we had some evolutionary engine running in a lab, a chemical soup experiment, and it actually evolved life. You know, how would you detect it? And that's really where we've been focusing our energy, is actually thinking about the experiments in the lab where you have a de novo origin of life event driven by, you know, an automated chemistry platform. And if you can do a large enough set of experiments that you actually might discover a chemical system that starts complexifying in the way that we associate with life, how would you even detect it? And so that's where assembly theory came out of, was this actual issue of detecting in the lab an origin of life event, if we could even engineer one. But the thing that's interesting to me about that problem is that's not usually the way that we think about origin of life, because we're usually thinking about synthesizing specific components of it and putting all the control of an intelligent agent into the experiment to make things that look like what we already associate to life. And that's sort of a similar thing to what we're doing in this artificial intelligence space also, is we have some model in our mind of like the sort of, perception of what intelligence is based on what humans do. Like humans communicate through language, and therefore if we just engineer those parts in a box, we'll make artificial intelligent systems that are equally as intelligent as humans. And obviously that's a huge debate right now, because as we're developing this kind of technologies without that deeper understanding of what it is to be intelligent in the universe and creative in the universe, we don't actually know what it is that we're building or how to even evaluate whether they're life or they're intelligent or not. So I think there's a lot of parallels between these problems, and I see it across a lot of areas of technology and fundamental science, where there's this kind of convergence on this set of problems of life and intelligence being sort of an existential crisis of our time that we don't really have a fundamental understanding for. And that also really motivates me a lot too, because I think these problems are just so important.
You've touched on a number of things, which I was going to get to, I hoped, as we go through it in the order of the book. But I mean, you talk about basically what you and Lee Cronin is trying to do in his lab at the University of Glasgow, right?
That's correct.
Chemify, the company that he has started, and what you've referred to as the Genesis engine.
Hmm. Yeah. Yeah. So Lee's really interesting. So Lee's the original developer of assembly theory. And what he was doing was he really wanted to build something that could do original life chemistry, but do it agnostically, like with no
Mm.
bias about the kind of chemistry life should be embodied in. And so when he started his lab in Glasgow, he started working on trying to develop technology that could do automated synthesis of chemistry, because he basically wanted a robot that could do a search of chemical space to look for original life to happen. And so I talk about it in the book as like building a
Hmm.
search engine for looking for alien life, basically, because we want a second origin of life. And so he's spent a lot of time developing this technology. The sort of foundation of it is called the computer, which is built on the principle of computation, which is related to like fundamentals of computation. Not to get into too many details, because I think it's actually like a very deeply fascinating uh, uh, on a philosophical terms,
Mm.
that we have computers that can do universal computation. They can compute any computable function, but we haven't built machines that can make any buildable object. This goes all the way back to von Neumann and his idea about self-reproducing
Yeah.
machines in the sort
Yeah.
of early days. So what Lee had envisioned was a like a robotic architecture that could do any chemical synthesis. So it's basically a universal constructor for chemistry, some universal machine. And if you had such a machine, then you could actually do the search problem for an original life event. And so that's the technology he built, but it turns out to get it funded, he had to promise people he could make drugs on demand.
Right.
So it's like a 3D printer for drugs and drug-like molecules. And this becomes interesting because, you know, part of our shared vision on developing assembly theory as a theory that allows us to explore the original life in this laboratory-based way and actually have a theory coupled to the experiments that we might actually be able to validate, you know, when we solve the original life, and in the way of, you know, true marriage between theory and experiment. Like you want, if you're talking about theoretical foundations and you're talking about something being deeply embedded in the structure of reality in the way we talk about in fundamental physics, you have to be able to experimentally test it. And it has to be, the abstraction is embedded in the experimental architecture. You have to be talking about real molecules and physical properties of molecules. Um, so so we have this vision of doing original life that way, but the technology, you know, developed in an academic lab is not operative at scale to search large volumes of chemical space. So this became Lee's motivation for starting Chemify was, you know, like if I have a moonshot of building, you know, $1 billion company that can do, you know, scale this technology of robotic synthesis of chemistry, then we would be able to build large enough experiments to do the original life in the way that we think it might actually need to be done to be solved.
You say it might take millions of chemical reactors
Yeah.
running concurrently? Wow.
Yeah. So I think this is the thing that's super interesting though, because we don't know how much, you know, like if you could really build a Genesis engine and you could really search, you know, different kinds of geochemical environments and conditions and different kinds of orders of mineral addition and all the things that planets do naturally. We don't know how large of a volume of chemical space, like how many configurations of molecules in an environment do you need to explore before you have the original life happen. That's an unknown parameter, and I actually think of it as an unknown cosmological parameter, because if you knew that probability, you would be talking about how often it is that life emerges on planets universally in the universe. And so part of the reason I got really excited about this kind of experimental paradigm for the questions we have in astrobiology is traditionally we've thought, oh, well, we'll just go out in the universe and look for life. And when we find it, you know, we'll know the probability because we'll have a second example. But most of the ways that we construct our search are not really, you know, they're not informative if they have negative results. They're not constructed to actually constrain the probability. It's getting better with the statistics of exoplanets, because you can think if you know, survey hundreds of exoplanets and I'm looking for a particular atmospheric biosignature and I don't see them, then that rules out certain hypotheses about life on those planets, but it doesn't rule out life on those planets because we don't know enough about life to rule out life on those planets.
Exactly. Yeah.
So I guess I'm excited at the idea that you could have an experiment, and even if you're not observing original life happening in the experiment, you actually have experimentally controlled the conditions. So you can now start to bound the probability it could happen on a planet. And that's something that we don't know. So that could inform exoplanet searches, because it might be, we think right now we can look at 10 planets and we'll be likely to detect life, but it might be we actually need something that surveys 100,000 planets. Like, we don't know, or millions of planets, like, and so so I think this experimental theory program is actually really important for getting at the questions we want to do. And it's expensive. So this is why it's important for reaching out to technology and really thinking about the technological implications of the problems that we have in astrobiology and how we think about them.
I hope that, Chemify works out to be a profitable concern, just as, a certain guy who's pretty happy about the results we saw in the United States yesterday wants to get to Mars, but knew he had to do a lot of stuff in space before that.
Right. Yeah.
So.
Yeah. We kind of think of the Origin of Life as like the sort of moonshot project of Chemify, right? It's like its real purpose is solving the origin of life, but it has to go through these other things to actually build the capability. Yep. Yeah.
So as folks, as I glance away a little bit now and then, it's because I'm looking at the things that Amber is passing along to me in a private channel, but also a little bit at all this participation that you guys have underway in the chat channel. I promise to get to some of these a little bit later. Some of them will actually fit in with where I hope to take the conversation. But for the moment, please bear with me as I throw another one at you, Sara.
Sure.
And so here's a quote. To get to an answer for what is life, we may need to ask a different question. Why life? That is, we must transition from defining life based on a set of descriptors, possibly unique to our own Earth, to deriving life's properties from a fundamental theory of the kind physicists are known for developing, which not only explains what, but also why. This is necessary if we are to have any hope of solving how life first emerged on Earth, or generalizing our understanding of the possibilities for life that may lie beyond the boundaries of our own planet. This is very much what you've been addressing in the last few minutes.
Yeah. And I think just to add to that, it's interesting because I've gotten a lot of pushback in my career on a lot of things, I think, because they tend to be moving in a direction that we haven't thought about before. And I really like opening new creative spaces. I don't like competing on ideas people are already like understanding and working on, because I feel like if there's ideas that a lot of smart people are working on and they're not making traction, like I'm not gonna do better. So I like to try.
Or it's incremental at best in most cases.
Yeah, exactly.
Yeah, right.
So usually my intellectual strategy is to try to open new spaces. So it's been interesting to me, with this idea of life being a frontier for physics, that a lot of people will, kind of, take issue with that, because they say, well, we already have brilliant theories of fundamental physics, and everything else is just sort of an emergent phenomena or an epiphenomena. You don't have any evidence, you need new physics. But my counter to that is we don't have any evidence, we don't, because we haven't been able to solve certain problems with the ideas we have now and appealing to origins of life and alien life detection. But the other interesting thing is, like, if you accept that life exists out there in the universe, you're automatically saying life is a more general phenomena than what happened on Earth. And then you have to actually position yourself to talk about at what level of generalization do you actually mean. And you could mean that the exact chemical makeup of whatever, constitutes us emerges on planets. But I think for the reasons of how large the space of all possible molecules is and how complex things like DNA and protein are, it's very unlikely that you're going to get the same exact thing. So then you have to ask something that's a more abstract principle to get at universalities. And this is what physics does well. It tries to unify things that might otherwise look different with a very deep explanation that tends to be mathematical in nature, because it's very abstract and has to apply to a broad class of phenomena. So one of my favorite examples is just to think about motion. Like, before we had theories of motion, how would you possibly explain balls rolling down hills and planets in the night sky? It's very obvious to us now that mass and acceleration are the right variables, like the right abstract things that we can go and measure in the lab to talk about motion. But it could have been color, it could have been composition. Like, there were things that were candidates So getting to these universal descriptions that actually capture the essence of the thing you're after, like what is the abstract property we mean when we say motion, is a very non-trivial thing, and it seems very trivial to us now to have that knowledge. But you're thinking about life in the universe. If it's a universal category of nature, it must have some of these properties, because more than one thing has it. So it's really trying to look for that unification, like what is that deeper structure, that deeper theory that would be able to broadly describe all the things we might want to classify as life. And
so
that's yeah, go ahead.
You put us on the beginning of that road, the starting point, on this board game that leads to assembly theory.
Yeah.
And one of the first steps that you take in talking about this are what you call the 3 hard problems. Well, I'm going to have to do them from memory because I can't see my. Oh, here they are: consciousness, matter, and life. And we may not get into a lot of detail on all 3 of these, but consciousness in particular was really intriguing to me. You know, you talk about whether we can really understand consciousness. It reminded me something you said of a science fiction story that I read many years ago, which just as a sidelight in the story, one of the characters in the far future happens to mention to an accidental time traveler, oh yeah, electrons are conscious, of course. And and I was so intrigued by that, and I never thought I'd see something like this being seriously considered.
Right.
Except that you say in the book, perhaps consciousness is fundamental and therefore all matter is conscious. Whoa.
Yeah. So, I mean, this is a discussion that happens, you know, in the study of consciousness now, like a very active field of research. And actually it's becoming more active with people thinking about machine consciousness. So it's really interesting how artificial intelligence has kind of rejuvenated the consciousness field in new and interesting ways. But there's this idea called panpsychism that, you know, consciousness is so hard to explain. It's the subjective inner quality of things that exist, and therefore maybe it is the substrate that all reality is made out of. So the sort of panpsychist resolution to what's called the hard problem of consciousness, how do you explain subjective experience, is to assume that subjective experience is actually the most fundamental thing and everything else is derivative of that. I don't find that to be a good explanation, because I think if you're trying to explain something, you can't assume that's the most fundamental thing, because you want to explain it in terms of something else. But I think some of the ideas that they play with intellectually and philosophically in the space of consciousness studies and how they think about how this really difficult problem in science confronts philosophy and also what's knowable, leads to some really interesting insights into these questions. So I think these kind of thought experiments are critically important. And of course, we don't know, you know, what consciousness is. So it's open territory whether panpsychism is correct or not. But I tend to take a practical mode in my approach to science, and I'm really interested in, you know, merging these kind of theoretical abstract ideas with experiments, as I was saying. So for me, it's always like, what kind of abstraction can you build that's actually testable? So I like to take these questions and turn them into the sort of one that you might actually be able to get some traction on to get an answer, and not only pose the question, but have a question you can answer.
Which, of course, is one of the most exciting things about assembly theory, because it is actually a theory that is testable. We'll come back to that, but a word or two first about the concept of information and how central it is to all of this, which struck me as, you know, the ability, see if I got this right, the ability of life to create, store, utilize, and duplicate it. It really seems so key to everything that underlies assembly theory.
Yes. So when I started as a postdoc at Arizona State University, I was on a NASA fellowship and I was working with Paul Davies, and he really encouraged me to think, you know, what is the origin of life transition? And, you know, he's also trained in theoretical physics. And so for us, it really became a problem of what is it that we talk about in life that is not a category that we like a way of describing the world that we see in physics, and exactly what you described, this role of information actually having some causal influence on the dynamics of systems became the sort of thing that we keyed in on. And so very early in my career, thinking about the origin of life, it seemed to me that there was some fundamental transition that happens at the origin of life associated with the fact that information gets stored and it actually becomes consequential to what structures get built or how they can persist or how they behave. And assembly theory is a way of doing that I think feels very natural and is also testable. So some of the philosophical ideas I proposed very early on with Paul wouldn't work. So we talked about like these hallmarks of life. And one of the hallmarks of life, just to give a sort of brief glimpse into it, is this idea that the laws should change as a function of the state. So what that means in terms of physics is, you know, like if you go to any standard physics textbook or any dynamical systems theory, we always write an initial condition and some fixed law of motion. But if you get into biology, it's like you can't write an initial condition and one rule for the system to behave for all time, because like if you have something like a genome, you know, the genome reads out in, you know, proteins, and the proteins might change the state of the cell. And so what genes get turned on and off then change. And so the behavior can change dynamically as a function of the state. But that's sort of all, like, that's just a general dichotomy. But the issue is like those two things kind of fundamentally don't sit well together. You can always kind of reduce this one, the sort of idea of this dynamics of states and laws, into something that just has, I don't know, sort of larger scale laws. Like the mathematics, like there's some weird things about the compatibility of those, which I played around a lot with early in my career. And long story short, there were a lot of hallmarks that we talked about the role of information in life and how it connects to physics, that I tried really hard for like my first few years as a faculty member to try to understand, and I couldn't make any of them fit. Everything had holes in it. And I think assembly theory is super interesting because what it does is it actually makes information in terms of the history and the construction process of objects physical in the objects. And this is sort of a natural resolution to all of these sort of philosophical paradoxes of top-down causation and how can information be causal. Because you're basically saying these structures cannot physically exist without this kind of causal constraint in history to build them, this kind of evolutionary process. They had to have information in the past in order to exist at all. And it makes time like a critical component of it. And I think these were the things that were missing is actually time and history as physical features of evolutionary objects in a really fundamental way. So that's sort of how assembly theory resolves the dichotomy between what life is doing that's kind of weird, and does it in now a way where you can talk about this as a material property, which physicists like to do. So now we can talk about information, not just in a sort of abstract sense. And it looks like it has some ability to call the shots, but you've never pinpointed where it is in the system, right? If I have a thought, like where is my thought that's controlling my behavior? And this was always the problem we had, is like top-down causation. That's the problem. You have these informational patterns in DNA or in brains, and they seem to control causally what happens. But that's not compatible with standard physics, because standard physics would say it's all the way reduced to the bottom of reality, and its elementary particles can explain it all. And assembly theory says, you know, at the level of elementary particles, that can explain everything. But in order to get to something like us, you actually have to follow the sequence of steps and the set of constraints and the selection in the evolutionary history. And that is actually the physical feature of objects like us. So we're like very large in time as physical structures. And so you're missing that whole causal time dimension, and that's where life is.
I want you to know that I did your experiment.
Okay.
I turned the page.
Oh, yeah, you're my first actual confirmation. So that's very exciting.
I'm very proud.
Oh, that's amazing.
I mean, so, you know, for the few people out there who didn't read the book, I mean, you say, please do this experiment. And then you wrote in the book, turn the page. I did. And so information was causation.
Yes. Yeah. And I think this is the reason I really like that example is it also really plays with how information looks very non-physical across space and time, right? So if you want to say, like, I wrote that book, you know, I don't remember when I wrote that original passage, but it's probably at least a year ago now, you know, looking at the publication timeline. And to have you sit in, you know, reading the book and physically turn a page because I had this intention and this action that happened in the past, and actually it had the consequence, like that's the property of information being non-local in space and time that makes it really hard to pin down from the perspective of traditional physics. And I think what assembly theory offers is really taking account the time and the structure over time as one of the main explanations for why anything happens on our planet as an evolutionary process. That is literally the definition of, I guess, what life is in assembly theory.
And here we are talking about it again.
Yeah,
With creating yet more information.
that's right. Life is good at that.
There is another great concept, which I just absolutely love, and that's anti-accretion.
Mm-hmm.
Could you take us a little bit through that?
Yeah, so the term anti-accretion actually originally came from David Grinspoon, because he had this whole idea about.
Great guy. He's a friend, yeah. A past guest. And I loved your passage about his thoughts about the Anthropocene as well, or is it Anthropocene? Yeah.
Yeah.
Go ahead.
Yeah. So at the time, I was thinking a lot about what would be a good example that really could juxtapose like what we currently understand with physics with what I think is missing as far as us as observers inside the universe, going back to like original part of our conversation. And really get that point across. So anti-accretion, I think, is just one of the best examples of it. Anti-accretion is basically the fact that our planet is launching satellites into space. So if you kind of decenter us as humans and intelligent things, like, because we can see ourselves doing that, you just think, you know, there's a planet that evolved a biosphere, and now that there's a technosphere on that planet. That planet now has the informational capacity through evolution of, you know, biological forms into social forms that could learn laws of physics, can now launch satellites into space. So anti-accretion actually becomes a good example of an intelligence in the universe and what it's capable of.
A planet losing its own mass because of life and the technosphere. Yeah.
Right. And so the reason I particularly like this example is that like the example requires the intelligent things to learn the laws of physics. So, you know, Newton's law of gravitation is actually causal to satellites being launched into space, at least on our planet, because if he didn't come up with theories of motion and gravitation several hundred years ago, or somebody in that era didn't, you know, like somebody had to come up with those set of ideas in order for us to have these technologies and for that process to be possible on our planet and also to be reliable. It's not like, you know, a one-off anti-accretion event where we have like an asteroid hit our Earth and it ejects the material into space. It's something that's reliable and becoming more reliable on our planet as our engineering gets better. You know, at some point we're going to be launching rockets from multiple locations all over Earth into space, you know, for reliable human transport even. So presumably, hopefully, if we have a space
we're getting there. Yeah.
So the point of that example is really that it's not just that this process happens and it's a signature of intelligence, but our current laws of physics are not adequate to explain it because actually it's an evolutionary process that learned laws of physics in the first place that can do that thing. And so this is why I particularly love that example.
As do I. Without going into the other two hard problems, I wish we had more time. Matter, life, and consciousness. You distilled them, though, into a single question. And here it is. Why do some things exist or experience existence and others do not? Your mentor, who you've mentioned at ASU, Paul Davies, the man that I once almost got killed because I accidentally ran a red light while I was giving him a ride. He's thought a lot about this, hasn't he? You know, why?
Yeah, so Paul was an excellent mentor when I first arrived at, I mean, he has been through my whole career, but I particularly remember when I first arrived at ASU as a postdoc, he used to pose these amazing thought experiments, you know, just open questions that somehow revealed something very deep about the nature of reality. So he was talking a lot about Paulia's urn. And if you just thought about the great urn of all things that could exist and you were pulling things out, like why the laws of physics that we have or why any of the structures that we observe. And this is very deep in the foundations of physics. We don't know why the laws of physics have the mathematical structure they have. And so people have proposed all kinds of multiverse models that explore different mathematics things. So that was one of my favorites. So that was one of the things he seeded with me, like a whole bunch of these kind of things very early in my career that were very disconnected. And I think I always saw it as a challenge of like, oh, I have to grab all these things and figure out how they're connected to get to this deeper theory. So so that one really stuck with me. And I think when you're thinking about the problem of selection and what life does, like it seems to be the case that there are a lot of structures on this planet that only form on this planet. You know, this conversation being one of them. I don't expect this to emerge on any other planet. With
our evil twins, no doubt.
Yeah, right. So, but of course, there's a causal explanation for why we're sitting here having this. But that again goes back to the history and the causation, all the way embedded in the history, all the way going back to the origin of life matters as part of the explanation for why we're here. And every step of the way of biological well, just life generally, like for me, life is actually the process of the construction of the possibility space. And so, so life is constantly selecting out of this very large space of things that could exist, what gets to exist. And so you can think about this in terms of your imagination, which I talk a lot about in the book. Like, why is it we can imagine all these things that don't exist, and sometimes we can create them? I think that's a very non-trivial feature of our universe, and we shouldn't take it for granted.
Another one of the concepts, really a key concept, one of the few things that you put in italics in the book, brings up something that I'm also fascinated by. And here's what you said: life is the only thing in the universe that can make objects that are composed of many unique parts. We're zeroing in now on assembly theory.
Yes.
And defining objects, fundamental objects, seems to be another key to all of this.
Yeah. So I have had a lot of fun with a set of thought experiments around what's fundamental over the last few years that I ended up talking about in the book. Because when you train in a physics education, fundamental is the indivisible things that all of reality is made out of. And of course, you know, if you go through science education, you learn that atoms are called atoms because atom was the Greek word for indivisible. And when atoms were first discovered, we didn't know they had substructures. So we thought the periodic table, the elements was it. That was the bottom of reality. And those things are the atoms that everything is made out of. And then we learned otherwise. And so then we have elementary particles and subatomic particles. And of course, there are candidates that might be even more fundamental or more, you know, like smaller than those things. So string theory, for example, is one candidate that people have been very excited about in the past. I think there's maybe less enthusiasm now. I don't know. It seems to be waning a bit, but that string theory might explain the structure of the standard model because it would explain all the particles, and everything's made out of strings, which are much tinier than particles. But the thing there, the reason that we haven't confirmed string theory as a theory is because it's beyond our technological limits of what we can actually observe right now. And so it occurred to me that if you're really thinking about ourselves as an evolutionary process that's learning more about our universe and expanding our horizon of what we can measure and observe through our technology. So we have, you know, like we can perceive reality because we have eyes and ears. And then, you know, over many centuries of human development as a social creature, we developed things like microscopes and telescopes. And eventually those were the things that allowed us to, you know, like if you think about high energy colliders, this giant microscope, they allow us to see the interior structure of things. So I thought this horizon of what's tiny and fundamental, you know, is always going to be a receding horizon based on our point in evolutionary history. And so that struck me as really interesting. It came out of this thinking that really what's fundamental is all the things the universe has constructed, because those are the ones that you can actually learn about the laws and the mechanisms the universe has to build them. So I in some sense think, you know, these things that we talk about in fundamental physics are really the boundary of what we can know, and everything inside of that that's built out of them is actually what's fundamental to our universe and part of the intrinsic structure of it. And really part of the part that we, you know, we actually can understand the structure. And assembly theory deals with those kind of objects. It deals with the objects that are constructed by what our universe basically has some constraints or laws it operates by, and can actually construct these possibilities out of those laws. And to me, that seems very fundamental. So it's kind of an inversion of
Yeah.
the fundamental, because it's fundamental in terms of what you can measure and understand, not the limits of your measurement.
Who is it said objects building objects, basically all the way down, like turtles?
Yeah, that was it. Yeah, I think a lot of people have said that. You know, there's the infinite turtles. We even had a workshop in the Beyond Center, which was called Infinite Turtles or Ground Truth, which was really fun. But the question is, there a bottom of reality? I think it's a really hard question, and I don't, I think it's constructive to ask. But again, that gets into the space of like how you ask the question informs what answers you get. So you have to kind of move around the space of questions in that domain. Yeah.
The one that my 8-year-old grandson will love is the Lego example, because I mean, okay, let's take Lego blocks as fundamental objects. They obviously exist only because life exists. But, if given an unlimited supply, I suppose, of Lego blocks, how many ways might one build a Lego Hogwarts, you ask? And how likely would it be that you get two Lego Hogwarts, in a universe that doesn't have life to drive that kind of thing?
Yeah, so we have a kind of two important things in assembly theory that we talk about when we're trying to talk about quantifying life. One of them is what we call the assembly index, which is the minimal number of steps to build an object out of elementary parts. With Lego, it's easy to visualize because you have Lego building blocks. You can stick them together. You can take parts you've already built and stick those together to try to get to something like Hogwarts. And in chemistry, we just think about it in terms of atoms coming together and making bonds. So you can kind of apply the same principle. But this copy number thing is actually a little bit harder. Like, why is it that we think things have to occur in many copies to be a signature of life, and actually this informational process constructing objects over time? And that's really, embedded in the idea that as you increase the number of steps to produce something, the space of possibilities is also exponentially growing. So in order to get there, it's becoming exponentially rarer that you would observe something like very deep in what we call the assembly space, these assembly steps. So if you see evidence of multiple objects with very high complexity, it suggests that whole entire causal chain was selected to construct them. And this is why we talk about evolution, building objects deeper and deeper into the assembly space. So there's a really funny, on one social media platform, someone was, playing around with assembly theory idea, and they put like some Lego in a dryer. And you put a bunch of Lego in a dryer. And, because this is this sort of infinite monkey problem, or like the shaking Lego.
Yeah, sure, right. How soon do you get Hamlet if we had 100 chimpanzees working for 100 years? Exactly. Which brings in the element of time, which you also talk about how important that is, not just space.
That's right. But it's super interesting because, you'll get a few, structures that might have like a low assembly index, but even that you don't see them in multiple copies, and it depends on how many components you have. So getting very complex structures in high abundance is a very non-trivial feature of what evolution does. And what assembly theory has done is allowed mathematically formalizing that concept and embedding it in the way we measure properties of molecules. So we actually can think about molecules existing in this, very large combinatorial space, and talking about how much that space had to be constrained to observe these molecules. So that's how we talk about the nature of selection.
So I always thought that the answer to life, the universe, and everything was 42. Turns out it's 15.
Yeah, so that's an experimental number. I think it's probably approximately 15. I don't know if I would
give or take.
Yeah, no, that's fine. But it's 15 and 42. I guess they're they're not. Depends on the error bars. But the idea there came from this idea of the assembly index and copy numbers. So based on the structure, the mathematics of the theory, and thinking about this exponentially growing space as you're building, a complex object. So Hogwarts lives up here in some, unimaginably large space of possible configurations of the Lego that go into it. And then you might have something that's like, 3 bricks put together that any child might assemble. So in Hogwarts Lego sets all over the world, maybe that's been produced thousands of times already. So there's a conjecture we have that there's a threshold boundary above which you require evolution and selection to observe objects in high abundance. And what Lee's lab did was they took a whole bunch of samples of non-living and living things and fossilized samples, and they got some blinded samples from NASA that were meant to kind of confound the experiments, and they were able to show that there is indeed a threshold, and it happens to sit at about 15 for covalent chemistry that we find on Earth. And above that, we only saw molecules that were produced by living systems. So as experimental confirmation of this conjecture we have in assembly theory that life is the only mechanism the universe has to build complex objects in high abundance, where the complexity has to be formalized in this particular way that we call the assembly index, because the assembly index retains this concept of memory and history to construct objects, and also physicality of like what's actually possible to build.
I've been hogging this so far. And so, Sara, I mean, do you have we are at an hour. It has gone so fast. Do you have a few extra minutes that you can stick around?
Yeah, I do. Yeah, I can answer more. Yeah.
Thank you. I appreciate that, because there's more of my own stuff, but I do want to get to some other people's things. I'll skip some of the stuff that I had. I think you've already talked about it, the assembly index. And this 15, I mean, really what is so wonderful about this, what makes, at least in my reading, assembly theory truly a theory and not just some idle speculation, is that it's testable. And that NASA is actually, as you said, been helping to do this by giving Lee Cronin some things to sort of play with.
Yeah, I think that's also why I got excited about it. So as I mentioned, like early in my career, I was thinking very abstractly about the nature of information in life and causation. And when I met Lee was trying to think about how do I measure life in the lab in a real practical sense. And he was doing these thought experiments with mass spectrometers and how he could measure the amount of evolution or causation in the experiment. And so that's when we really started working together on the development of assembly theory, because it's way more powerful to develop theories when you can actually test them. And there's like, and in a really rigorous way. I mean, the science, like I've become obsessed with the science of measurement because it's so non-trivial to do good measurements. And I'm like reading about the history of temperature. Like temperature was so non-trivial to develop as a measurement. Yeah, so that whole process coming into it is super interesting. But the long story short is, assembly theory can be tested because of the rigorous kinds of experimental embedding of the theory. And the first test of it was this idea of a threshold, but there are other conjectures that we're working on that the theory would propose that are also testable. So I'm anticipating there will be sort of a broad suite of things that the theory becomes useful for, from drug discovery to like trying to predict when the origin of life transition might happen in different kinds of material substrates. And those are things that we're exploring. And that's what makes it exciting, because if it's a good theory, it should be useful in a lot of different spaces. Yeah.
Let me go on to aliens and even possibly aliens among
I
us.
love aliens.
I've been trying to imagine a truly alien form of life ever since I was a kid, and I've totally failed. But then I guess so do most scientists, from what you've said. And then there's AI. We've got a question here from Kareem. How do you separate your definition of life from conscious life, e.g., AI? Is that conscious based on your definition of life? I was going to ask you, you do address it in the book, is AI alive, or is it approaching that?
Right. So I would pose the question of whether it's life, alive, and conscious as slightly different questions. And I think one of the things when you're working on foundations of science is you become acutely aware of semantics and like trying to be precise. Because these words don't have very precise meanings in a technical sense. So we're all kind of fishing around these common concepts.
Yeah.
But my conception of life, which comes from my thinking in assembly theory, but in particular, even before that, just trying to generalize life at the level that I'm doing, is that technology is life, because technology requires an evolutionary process to emerge on a planet to construct it. So my view of the technology on our planet is it descended from Luca by the same kind of fundamental process that we descended from Luca. Now, I also think that of inanimate objects like I don't know, I always have mugs near me or cell phones, like my cell phone, like if a cell phone's on Mars, you find it on Mars, it's a biosignature, right? It's not, you're
Yeah,
not
yeah.
spontaneously emerged out of the geochemistry of Mars. So the sort of amount of time necessary to go into the construction of a cell phone is a feature of the cell phone in assembly theory. And cell phones are artifacts of the physics of life. They are manifestations of this idea that information had to be acquired over billions of years to construct this object. Now, that's true also of artificial intelligence. It's very obvious that if we didn't have several centuries, well, many thousands of years of development of human language, then many centuries of development of lots of texts of written human language, and then the theory of computation emerging and having computers, and then, like all of the volume of data on the internet, large language models would not exist that could articulate things in human language. They're a direct causal consequence of this chain of events that humans have been building over many centuries. Now, the question of whether they're conscious or alive, they're definitely life. The alive or conscious question, I think, is much more interesting. And I don't know exactly where I stand on that question, because I think it depends on where you draw the boundary around what you're talking about. And this goes back to definitions of life. And the way I talk about it in the book is a lot of the issues with defining life are you're drawing a hard boundary when there is no hard boundary, because life is about this process that happens over time. So that's sort of one issue in this space. But I will say that as far as what assembly theory says about conscious entities, it's not a theory of consciousness, but we do have a lot of conjectures about what we think consciousness is in terms of what assembly theory would say about it. And, eventually, hopefully those will also lead to experimental tests if the theory, plays out in the long run in the way that we're hoping. But conscious systems are ones that are very deep in time. Because they have very large causal structures, a lot of history in the structure of that object. So I sometimes think about like human minds as largest causal structures in the universe, because they're just so causally deep. They're, like there's 4 billion years of evolution compactified in our heads. And I don't know that large language models have some of those properties that I would associate with that. It's kind of a long-winded answer to get to I'm not sure they're conscious or AI is conscious yet, but I think there's a lot of potential that these technologies could become alive and animated or conscious. And this is one of the reasons that I think we really need to nail this boundary between non-life and life and understand when it happens, because I think the origin of life is a process that can happen continuously on a planet and has happened continuously on our planet. And it might be happening in our technologies right now, and we don't even know.
I'm sure a lot of people have asked. I mean, I asked Siri, I guess you could ask ChatGPT now, are you alive? And if you say yes, are you lying? Or if you say no, are you lying? Sticking with that theme of AI, Stephen says, consider an exoplanet with a global AI network that can communicate electromagnetically with other planets. Would the AI network be considered life even if no biochemistry is involved? But that also presupposes, as you said, if the AI exists, unless there's some model that we don't know anything about, it is part of this gigantic long chain through very likely billions of years.
Yeah, so I think it's really easy to do thought experiments on things that exist outside of evolution. So we, in physics, we have this idea of a Boltzmann brain, which is a brain that just spontaneously fluctuates in existence without a body. And that's a really important thought experiment in physics. And some people think, they could be physically real based on quantum fluctuations, but we have no evidence for them. And I actually think they're physically impossible. I think the only way that the universe builds things like us is through evolutionary processes, not through spontaneous fluctuation, because you can't compress billion years of construction history if all of those events have to happen in sort of a particular order into fractions of a nanosecond for like a brain to fluctuate into existence and fluctuate out. So I think that we have done a lot of thought experiments that are actually physically impossible, but they're consistent with current theories of physics. And this would be one of them in my mind, is that you can't just take, a modern technological structure and assume it's going to exist autonomously in the universe without the entire history that built it. So to me, biology, the fundamental unit, is these lineages of the information constructing these objects over time, and they don't ever lose all of that history.
Besides, I prefer to believe that we've actually had this conversation over the last hour. We didn't just pop into existence a millisecond ago.
I'm pretty sure. I don't know.
Might as well. Joseph asks, and this is actually one that comes up in the book. He says, Max Tegmark, I think he means Tegmark, defines life as information that can preserve itself and replicate. What do you think of the merits or limitations of defining life this way? And this also brings up that definition of life that you point out that a lot of people think is the NASA definition of life, but it was never made of like the official, this is the official word from on high in headquarters at NASA.
Right. So replication tends to be foundational to many definitions of life. And I've come around to thinking that replication is kind of a derivative process of the more fundamental mechanism of what life is. And the reason being, because it's like the replication is kind of what is life. And if you're asking why life, replication is part of the explanation about why life, but it has to be embedded in sort of a broader set of principles, I think, about the nature of life. So the universe doesn't, not everything can replicate, not every pattern. So you actually need to have selection happen before you get replicating patterns. And to me, selection and thinking about the construction of the space and then is more important. And then replication becomes patterns that are preserved out of that process. So it's critically important. It's almost an emergent property of what life does, which is pretty deeply intrinsic to it, but it's not the core feature you want to go after if you really want to have an explanatory feature that explains the emergence of replicators on early Earth. Like you can't start with replication because that's, putting the cart and the horse at the same time. It's not even the cart before the horse, it's just get them all miled up. And this is a big problem in Origins of Life because we don't know what the first replicator is. And what assembly theory is saying is like there's an evolutionary process that's selected to get to a replicator.
I'm going to throw a couple of aliens at you. Have you ever seen or maybe read Andromeda Strain?
I know of it. I haven't directly. I probably have watched it. I know I haven't read it, but I have a terrible retention for movies. I don't know why. I just don't remember them well.
If you happen to watch it, I would love to hear what you think. The life form, the alien life form in Andromeda Strain, at least in the movie, I can't remember if it's the same in the book, is basically crystalline, and it appears to be alive. We had a question from Dan about a virus. Is a virus alive? Well, a virus obviously needs other life to be able to replicate and do its business. These crystalline entities don't need to. And speaking of crystalline entities, there's a big monster in a Star Trek Next Generation episode, actually a couple of episodes, that is also crystalline. And does that bring up any thoughts? I mean, you think of the structure of a crystal as not being all that complex, really.
Yeah, so I think crystalline materials were critically important in the origin of life. So there's a hypothesis that was put forward by Graham Smith decades ago about mineral takeover, and that minerals were actually the first genetic material, and then sort of aqueous chemistry adopted memory later on. And this is actually something that we're really pursuing, thinking about assembly theory, is trying to understand, we've done assembly theory for covalent chemistry, doing it for minerals, and really understanding the structure of evolution and selection as embodied in crystalline materials is a very non-trivial problem. But it's we've made a lot of headway on it. Lee's lab has a couple really excellent people that have been working with him closely on it. And one of the things that I'm really interested in doing is applying that to these ideas that have been out in the community for a little while on mineral evolution and things, because I think people do think minerals evolve, but you can't apply standard evolutionary theory. And I actually don't think they're capable of evolution in the same way that evolution is a very substrate dependent process, depending on the structure of the material. And the material as described in assembly theory, I would mean it in terms of the sort of causation embedded in the material, which we call the assembly space. Those are more technical things, but if you think about evolution as a substrate dependent process, some substrates are better at it than others, and crystalline life forms, I think, are a little bit limited in what
I
they
bet you wouldn't
create.
mind being surprised, though.
I would love to be surprised. I mean, if I'm wrong, that's a great day, because if are changing, like that's what I'm here for. So So I really I love the idea of exploring and understanding things in new ways, and being wrong is sometimes part of that. It really challenges you to change your mind. I think that's the most beautiful thing that we do as scientists, that we get to change our mind on a daily basis. I love it.
I got to bring it home with a couple of self-serving references to our co-founder, Carl Sagan. One of them directly made by you, but I'll get to the first one that didn't specifically mention him. You have that lovely little second-person interlude in the book that stars Albert Einstein. And it made me think of that great quote from Carl, "We are a way for the universe to know itself." Your book has given me an even deeper appreciation for that quote.
That's awesome. I love hearing that. Thank you. Carl's been a huge inspiration to me, like many people. So yeah, really amazing.
So here's the other one where you dare to challenge Dr. Sagan. Sacrilege. It is not that extraordinary claims require extraordinary evidence, as Sagan put it, but instead we need to recognize that extraordinary claims require extraordinary explanations. The actual empirical evidence can be quite simple. What matters is how the evidence is connected to an underlying explanatory framework and how this interconnects to many of our other observations of the physical world. I like to think that Carl would have gone, yeah, very interesting.
Yeah, I hope so too. But I think it goes back to, there's a lot of things in the book where I'm challenging what I've heard from someone else. But I think that goes back to like what we do as deeply curious intelligences in the universe when we're asking the kind of questions we do. Like, I love to be challenged. And I love it when the way people think challenges me and forces me to think differently than I had before. So I think the intellectual debate is healthy. So most of the people in the book that I actually challenge, like, they're in the book because like it really was like intellectually stimulating for me, and it's kind of a compliment.
I got that. Yeah.
Yeah. So maybe he would have liked it, but I think. I don't know. I can't speak for him, but
we can ask Andrew someday,
yeah.
Who's also been a guest on here with talking about contact. Speaking of discovering aliens, so I want to make sure I go in the right direction here as we finally wrap up. And finally, of course, origins. As you say, no one has yet created life in the laboratory. Lee Cronin is at least taking the early steps toward that with your collaboration. And I mentioned that you say in the book that it could take millions of chemical reactors and Lord knows how much time. You say you want this to happen within your lifetime, which is something I also hope for. I know that our CEO, the science guy, is hoping for exactly the same thing.
I think a lot of us are rooting for this outcome.
Yeah, right. I want to be here. I mean, I think you say, and it's in the closing, you want this to happen within, your existence, within your current lineage in this grand procession of life. Do you think it's realistic? Do you think that we are making enough progress, or that we might be able to achieve the promise of assembly theory?
I don't know, but I think because it depends on, I think doing the work and putting the real work in, like, it's a lot of work to build ideas in this many spaces, a huge network of collaborators and people really working and focusing on this problem is necessary, right? And then the challenge with any kind of scientific enterprise is you don't know if you'll succeed. So I think the best I can say to that is, we're working super hard, many of us, to try to figure out how to make this happen. And I think the likelihood of it happening just depends on how much we can invest in this space in terms of intellects, like people wanting to think in ask these kind of hard questions and really try to pursue the fundamental science, and also in terms of like, how do we get the investment in the space to really make it happen. But I think I'm optimistic because I think so much has happened in a relatively short time scale of my career. So when I started working on origins of life, theory was really like the kind of theory I'm talking, like fundamental theory that really would explain the transition from non-life to life. Like no one in the field was really talking in that way. There was a lot of stuff on prebiotic chemistry, and there was a lot of stuff on reconstructing LUCA. And now it's like, a lot of the field is narrowing in on the fact that we might actually be able to formalize this transition and test things. I think that's a radical transition in the span of, about 2 decades that I've been thinking about this problem. Yeah. So to me, that's incredibly promising, because that means that things are moving. And what is, like actually another Leeism, I really like this one, is like, like the ultimate peer reviewer is reality itself, right? So like we're not competing against each other. We're competing against reality for some fundamental understanding. So it's either there or it's not. And I guess that's sort of our, the way that we think about it is like, we really want to understand. And understanding will come if it's actually, it's real. But I think all all these signs are like incredibly promising, which is why I'm so focused on developing it the way that we have been developing it, and putting a lot of intellectual work into it and a lot of passion, because I think it's incredibly exciting.
I certainly think so. Just a couple more. I do want to give a kudos to Craig out there, who kind of brought up the same thing that I did, that great quote from Carl about we are a way for the universe to know itself. And then there's another one that I'll get to in a moment that has to do more with ethics. But I don't have to tell you that the book and assembly theory have generated a generous share of criticism. Some of it strikes me as way over the top and even ad hominem. But then there's some more thoughtful criticism, like there's an essay which I did share in the community, and I think Amber has a link to. If she hasn't put it up already, she might just be able to do that. And I think you're familiar with it. An essay by Johannes Jaeger, titled Assembly Theory, What It Does and What It Does Not Do. You're kind of in the hot seat on all of this, you and the other proponents of assembly theory. What are your reactions to all of this?
I think it's exciting, and it's interesting to work on a set of ideas that so many people are going to react to in so many diverse ways. So that part's been kind of very interesting, because it's really surprising to me in the multitude of ways that people have engaged with this set of ideas. And also, if you want to do good science, as I said, you have to engage with the criticism. So ones that are ad hominem and like some of them are just aggressive, and for some reason, assembly theory is, a personal affront to some people as a new idea. But right. Yeah, so leaving those ones aside, you want to pay attention to the actual valid criticisms. And actually, this is one of the reasons that both Lee and I are so public about the work that we're doing, or at least this is how I feel about it. Maybe Lee might say something different, so I think I'll only speak on myself. But I think the more feedback we get, the more we can improve the ideas on a more rapid time scale. So, and actually get to those kinds of answers. So for me, the heat is actually like that's reality testing you, because it's not just the experiments that test you. It's like if you have like all of these people paying attention to the ideas and they're all putting it under critical inquiry, like they're either going to hold up or they're not. And that's exactly what you want. Like if the ideas don't float, they're not going to float. I'm not like, I'm ready to change my mind tomorrow if somebody gives a convincing argument. So the Jaeger paper is kind of interesting because it's a philosophical criticism of a scientific approach to the problem. And I think there are some things there that are really just people have certain sets of ideas epistemologically about what they think the fundamental nature of life is. And we're really trying to start with like a theory experimental approach and build into some ideas that I think are also very fundamental to the nature of life. And I don't think that the things are at odds, but it's really early stages for the theory. And it's also important to be aware of like, what are the experimental tests, because the falsification is going to come from the observations and experiments and whether it matches there, not whether the theory conforms to our a priori conceptions of what we think life is. And this is true, again, going back to the history of physics, it's like people don't want to accept quantum mechanics, but it's like the experiments are there. I'm sorry, that's just how reality works. So, So my
What was it, Nils?
philosophy has.
What was it Bohr said to Einstein when he said God doesn't play dice with the universe? And Bohr said, you know, Albert, who are you to tell God how he should run a universe?
That's exactly right. Yeah, so it's interesting because I've gotten a lot of comments that I change my ideas every couple of years, but it's because it's updated by new hires. I think assembly theory is collapsing a lot of them down, but the way I talk about things is constantly changing because I'm constantly learning from the way that we're doing things, and everybody in our collaboration is like that. So critical feedback is great. And nobody's more critical than the people on our teams. I can tell you, they are like picking apart everything. So really, you want to hold yourself to the fire. Work with some smart PhD students. It's a tough.
That's science. That's science at its best. I better let you go. I've kept you longer, I think, than we've kept just about anybody for one of these, and it's late. Sara, I will say again, the book was exciting and challenging and stimulating, and it has changed the way that I think of the search for life, how it may have gotten started, and even understanding ourselves, life, the universe, and everything. So I thank you once again for joining us, but most especially for this book. And please tell Lee Cronin and all of your other colleagues that we wish them the greatest of success as you continue to develop this theory and find ways to see if it's going to help us understand the reality we share.
Thank you so much. Really lovely to be here.
And to all the rest of you out there who have stuck with us through this, whether you're watching the recording or you've been with us live, thank you again. We are going to be back in about a month. We're already into the month where we are considering this book, Re-Entry, by Eric Berger, Space Elon Musk, there's his name, and the reusable rockets that launched a second space age. And I can tell you, a couple of people were thinking, oh, he's just one of those big Elon fans. No, he's not. Read the book, folks. He recognizes the accomplishments that Elon has made, but he is very straightforward about some of the failings of that guy who has revolutionized access to space and isn't done yet. Anyway, we'll be talking in early December with Eric Berger, that great space journalist and author. Sara's book, I'm going to go back so that I make sure I get it right. For those of you who haven't picked it up yet, why not? It's Life as No One Knows It, The Physics of Life's Emergence, and it was published this year. Again, Sara, thank you so much, and keep up the great work.
Thank you so much.
Take care, everybody. We'll see you again soon here in the community, and thank you for your support, your membership, which makes it all possible. Take care, everyone. Bye-bye.
Bye, everyone.